It's on. Okay. Okay. Yeah, just last time there was some audio message that it was recording. All right. Yes. Okay. Well, today, what I wanted to do is that I wanted to go through the lab 5 with you, and also to discuss the reconfiguration. And I wanted to use that paper that I shared with you. This one, the reconfiguring a state machine, which is kind of not an, it's like a more research-oriented paper, I would say. It's not like an engineering paper that will tell you exactly how to implement the things, but still it will give you some idea of what you should do in Lab 5. And well, according to our lecture plan, we should have had a lecture on Bitcoin today, but I will postpone this, and I will also close my Discord. So so we will most likely do this after the Easter break, because well, soon it will be the Easter break. And also I promised that I would be finished with the project description for today, but that's not true because I didn't finish it. So I'm gunning for the next lecture that it will be finished. So anyway, yes. So and I saw also that a lot of you did manage to finish Lab 4, and that's very, very good, because now you have a very good foundation to do the last 2 labs, and also for the project report. So yes, about Lab 5, it has 2 main parts. The first task is to basically use your Paxos or multi-Paxos implementation and just extend it to not allow arbitrary values, but say that now we will only accept values that is which is like confirmed by some invariants corresponding to the bank application. So it means that you can, for example, only withdraw some money if you already deposited a similar or at least such high amount. And this is a nice nice use case that you can use multi-Paxos for. And it's like the smallest part of the lab. So don't make the mistake of thinking that this lab has 2 tasks and they are roughly 50% each. No. The task 1 is much easier to do than task 2. So unless there is some specific questions regarding task 1, I will jump directly to task 2, because that's the difficult part. And this is the part where you have a lot of freedom of doing what you like, because we didn't give you like a very defined interface of how you should implement this. So you are free to pretty much choose your how you would like to implement this, but also this will be more difficult for you because you have you are not given a easy starting point. So for this task, we will accept many, or we will accept a lot of different solutions, and the main idea here is that is not that you should be able to implement a reconfiguration protocol in every possible failure scenario or any possible thing that can happen, but you should be able to implement a RIF configuration protocol on top of what already exists, and you should yourself be aware of the limitation of your implementation, that it's working in this and this scenario, but in some other scenario it's not working correctly, and we will be reasonable in approving the lab as long as you are aware of your own or the limitation of the implementation. Yeah, so if you followed along with the labs, you know that when we say reconfiguration, we are talking about changing the members in the execution of the protocol. And for our case, it means that we are adding or removing Paxos instances between each execution of the system. And as you know, that we sometimes we don't have control over when nodes are failing and when they're coming back. So this can also happen like during the execution, and this is where the complication can start to arise, because if you imagine that reconfiguration could only happen in some time period where there was nothing else going on in the system, then it would be much easier to implement. But since you have you can have a lot of things going on concurrently, it makes the whole thing more complex. So we put the let's say the approval guidelines, as I said, very broadly, and the minimum that we want from you is that you introduce a new command, which is a reconfiguration request. And the reconfiguration request, it needs to the request contains what servers will be part of the system from now on. So, for example, the client can ask that now I want to scale the system from 3 clients to 5 clients, or scale down from 5 clients to 3 clients, or any number in between. And you are free yourself to think about what's a reasonable approach for this. For example, can all the clients do this, or is it only, for example, one client? Does he need a special password or something? just use your own imagination of what you think would be appropriate. And as a minimum, we want that you demonstrate to the TAs that the system can first reach a consensus with when you have 3 packs of servers, which handles only one failure or masks one failure, and then we wanted to scale it to 5 participants, show that you can have a reach a consensus value when 2 nodes are failing, because when you have when you scale up to 5, you can allow that 2 crash. And then with 7 we can allow that 3 crashes, and still we can reach consensus. So we want that you will show this, and also to scale down, which is also maybe more difficult to. It's difficult or it's also difficult to scale down, not only up. And yes, we put 2 links here. I guess it looks like they're pointing to the same thing, but anyway, I wanted to go through the to this paper with you, and please ask any questions, just to give you some ideas of how you should do this. And I don't suppose that we will spend a lot of time, unless you have some questions, because if you're not asking any questions, I will just go through it very fast. So be prepared. Yeah, so I will skip the chapter 4 because it's talking about different protocols, and we don't need to be confused with too much things. And the author of this paper, this is Leslie Lamport, and he is also the author of the original classical Paxos protocol that you already implemented. And yes, so the first line here, reconfiguration means changing the set of processes executing a distributed system. So this is exactly what we want. And the paper goes on to let's see if I can mark something. Goes on to discuss on a high level what is it, and if I can have a little bit thicker line. Let's see how I do that. So it was 2. Right. So you see here, distinguishing a process failure from transient communication problem is often a challenging engineering problem. So, already on the 3rd sentence, it can be confusing. What is he talking about here? But here we are talking about basically a network delay or a synchronized network. Well, that's how I interpret it. Because a transient, it means something that doesn't last for a long time. There is a problem there, for example, a communication problem there for a while, and after some short time period, it's it's working again. So that's why he is saying here that a process failure and a communication problem can be difficult to distinguish, because of course when two servers cannot communicate, then the first thing that they can think is that the other one has crashed, but it might just be also that there's a problem with the network between them. And yes, he goes on to talk about that we shouldn't wait too long, and also we shouldn't, and also we should do something about it if it lasts for a long time. And one of the possible things that we can do, for example, if in the case that some parts of the system goes down, then you can kind of bring more nodes online. So if you're faster to bring things back online or new nodes online, then you reach like a critical level, then the system will continue operating. So remember, in Paxos we have this, we need 2F+1 acceptors, and this basically means that to handle one failure we need 3 nodes or 3 acceptors online, and as soon as one crashes, we can continue to make progress with only 2, but we can no longer handle any failure. So as soon as one of them crashes, the system will be stuck or have a live lock thing. So yes, so what's the idea of the state machine? It is this irrecoverability of output. So when something is decided, or not, I said irrecoverability, but it says actually irrevocability. So it means that you can not, as soon as the system output a value or writes a value or decides a value, then the system will not go back on it and say that I want to take back that value. No, as soon as something is decided, then that value is locked. And this if you took the blockchain course, or if you read anything about blockchain, then this is also something that you will see again and again and again when you read about blockchain. So exactly this irrecoverability property is much more highlighted in blockchain systems, but actually it must also be present in any state machine. And of course, blockchain is a state machine. So yes, then this paper talks about 2 approaches. What he calls the state machine approach, and which of course he says this is easy thing to implement, and another one is what he calls, I guess, the terminating state machine. I guess terminating the state machine. So yeah, we will discuss these two, and also for your lab 5, you don't need to. We don't expect you to implement the reconfiguration protocol to handle malicious failures. So just crash only faults is more than sufficient if you are able to do that. All right. So the state machine, as you already have implemented, the basic definition, if the pair C or the tuple CS is mapped to the pair O and S prime, then we say that the executing command C in the state S produced the output O and changes the state to S prime. So basically, if there is a map from this tuple to this tuple, then the command C gave the output O and changed the state. So this is like a typical way of seeing the state machine, that it goes from one state to another. And also there's a no op special command that doesn't produce any output and leaves the system unchanged. And this no op command is basically used to fill a buffer or increase the ballot numbers or something to make the system have some progress. All right. All right. So yes. So I don't know if there's anything more I want to say here. I'm sure you already know about the Paxos, and please stop me if you feel that you have a question, any question. And let's see here. And there is one small section here with the garbage collection and kind of interesting, since I just mentioned blockchain, but this problem is definitely also present there. And again, this paper doesn't explain to us what we can do about this. It just says that that if we keep maintaining the state and the entire state machine, the memory usage or the stable storage usage will just increase. So we need to periodically create some checkpoints or snapshots, and then delete the old consensus instances. So again, if you want to implement something like that, you're free to do it, but this is not the main point. So don't be confused about that. That part actually is not so directly related to the reconfiguration part. All right. So for the for the solution one that he proposes here, and the most simple way is that in the easy approach, reconfiguration is achieved by using different configurations for different instances. We define the configuration at command number I to be the one used to execute consensus instance I. So how does this work? The easy way to obtain a reconfigurable state machine implementation is to introduce a component config of the state machine state that specifies the current configuration. And the idea is that you send this configuration command kind of to the instance as an additional parameter to tell to the system that I want that this kind of servers will be my members in that instance. Yeah, the obvious way to define the state machine is to let executing reconfig with the configuration C, set config to C, so reconfiguration occurs immediately. We call this method R1. But then the problem with R1 is that it prevents concurrent processing of different proposed commands. Because, of course, if we change the configuration, then whatever commands was already like proposed or running concurrently, they cannot terminate, or at least they cannot reach consensus in the way that we want. Yeah. Since the configuration used to execute instance I+1 of the consensus algorithm can be changed by executing command I, the state machine implementation cannot begin choosing command I+1 until command I has been chosen. All right. And then to allow concurrent processing of commands, we define the state machine by introducing additional state so that reconfig C as command number I causes config to change after executing command I plus alpha plus I for some positive integer alpha. This basically means that you will propose that a reconfiguration happens in the future. So you can say that we want to reconfigure, for example, 3 instances later, if we have alpha to 3, or 5 or 100 or whatever number is appropriate, and then you can allow that many commands to run concurrently. And then if you want that the reconfiguration happens right away, you can use this no op to kind of fill or propose like a lot of values that doesn't change the state. Yes. So that's that, and So that's the what's called the easy way, and you can choose this way if you like to. And then the reconfiguration made harder with what was called the terminating state machine approach. It identifies that this algorithm here, R alpha of section 2.3, has the practical drawback that a reconfiguration introduces a sequence of no-op commands of length of alpha. This can be inconvenient for large values of alpha, for example, 2 to the power 64. So that's a ridiculously high number, I guess, but yes, so with that simple approach, there is some bound on the concurrency. And then the hard way is to allow that there is any number of commands can be chosen concurrently. So that's the main difference between these two approaches. That the simple approach, it has a drawback with the upper bound of concurrency, whereas the harder one has like a theoretical and unlimited. So yes, it then has three problems or three things that must like three orthogonal problems. First, stopping the current state machine. The second one, choosing the configuration to implement the next state machine. And lastly, combining the sequence of commands chosen for each separate state machine into a single sequence. Yes. So the stop sign method here, it adds introduce a new command, which is called stop. And what this does is that every state machine command that happens after this stop sign, it has no effect. And it has kind of the same idea that we can delay the stop sign if we allow, for example, up to alpha to be chosen. Then to stop the if we have some alpha, then the client can kind of pad the state by propose no-op commands or propose a lot of no-op commands. And lastly, the last piece of the puzzle is what is called the brick wall. The stop sign and the padding methods use the underlying state machine implementation, so their correctness follows immediately from the correctness of that implementation. However, they may seem unintuitive, the stop sign method, because it can choose commands that are never executed by the state machine, and the padding method because it fills the sequence with infinitely many no commands. We now describe the brick wall method that is conceptually simpler but requires a new state machine implementation called stoppable paxos. So there's another paper here in the bibliography with 14, and we can take a look at that. If you like. So the next part here, it talks about like here, it talks about the classical paxos, and it's I'm sure that you will be familiar with this. There's one thing to keep in mind here, that here he's using the ballot name, and in our wording we call this around. So ballot, this is around. It can be confusing. And so and also here, for example, it's more academically described with that a newly selected leader chooses a ballot number B it believes to be greater than any already used, and it begins ballot B by sending a phase 1A message to the acceptors, who responds with the 1B message. So you know that in the labs we actually implemented this the ballot numbers to kind of be deterministic, that we always increase by 3. But of course, this is not a necessity that you increase by 3, but you can actually, the main idea is that you use a round number that's higher than what was already used. Yeah, and then there's the response given back by the acceptors. So if the acceptors already sent an accept message for a command, they will reply back with that command, and if they didn't, they will not send a command back to the proposer. Yes. So yeah, stopping paxos prevents the leader from proposing a command if stop could be chosen as a lower numbered command. To describe how this is done, we first define xi bi for ballot B with consensus instance I to be the command C of case P1 above, and to equal no value in case P2. Stopping paxos places the following 2 additional constraints of what command a leader can propose in ballot B of instance I. So the first constraint on paxos, stoppable paxos, is that it cannot propose any command if, for some j less than I, it proposed a reconfiguration command in ballot B of instance j, or xi bj is a reconfiguration command, right? And then it cannot propose a reconfiguration command if for some k greater than I, it has proposed a command in ballot B of instance k or xi bk isn't the no value. So that's the constraints of stoppable paxos, that now the leader cannot propose any value that it wants any longer, but it needs to respect these two constraints. So let's go to the next page. All right, so we can go to the 3.2, choosing a new configuration. When changing the state machine implementation V to state implementation V+1, there are two basic ways to choose the new configuration that implements V+1. So one way is to let it be chosen by the configuration command executed by state machine V. So you say to the previous state machine what you want the configuration of the next one to be. It's kind of the most obvious one. Or two, we use a special instance of the consensus algorithm executed by the same configuration that execute state machine V. So I'm not so sure of how we would implement this, and it's also stated here that perhaps the option R1 is the most reasonable. Yes. All right. So combining the command sequence, we have shown how to initiate and execute of state machine implementations, all but possibly the last one being stopped. State machine number V is executed with configuration V. If a state machine has been stopped, it has a unique last interesting command. For the stop sign or brick wall method, that command is the first stop command. And then for the delayed stop sign method, it is alpha -1 commands after the stop command. And for the padding method, is this the last no-op command, and the definition is that let the eta v be the number of last interesting command of state machine number v, and defined eta 0 equals 0. Yeah, eta 0 equals 0. Yes. And all right. So in a naive implementation, each process would maintain a two-dimensional array of data where element of the tuple vi contains the data maintained for consensus instance I of state number v. Yeah. All right. So maybe that's what we want to cover with respect to that. Yeah. So in the reconfiguration methods based on the sequence of state machines, a state machine is stopped by proposing either a stop command or an infinite sequence of no op commands. So yes, you would obviously be more practical to implement a stop command to stop the Paxos execution, then to change the configuration and to start again. All right, so that's that. And as I said, I think that we can skip the different approach in group communication, and there is not so much more in this paper, except for the conclusion, which just says that the correction properties of the system, including irrevocability, follows from the definition of the state machine and correctness of the state machine implementation. Yes. And in this paper, they have only considered non-malicious faults. And you should, I would recommend that you also do that for your implementation. So that's that paper. We didn't have any questions today, so I don't know how to interpret that, but that was that. So is there anything that we should discuss more, or do you feel that now you are ready to begin the lab 5? Do you think everybody is content and good? Because we didn't have this lab 5 this task in previous semesters, so it's kind of a new task that we have given to students. So we are not 100% sure, of the difficulty and how you feel about this task. So that's we left it kind of open to allow you to explore yourself, about this algorithm, and we will not be, we don't have two strict constraints on approving these labs, because this reconfiguration is a difficult thing, and there's many things that can go wrong during reconfiguration, and there's many possible optimizations that you can do. So yeah, the main idea is that you will try and implement a working reconfiguration protocol that is working at least in these scenarios that we have explained here. And yes, you can ask questions anytime. But I guess the deadline for this is just like after the Easter, pretty much. So yeah, so yeah, it's the week after Easter. So yeah, just come with questions anytime, but I recommend that you start as soon as possible, because it can be tricky and can be difficult to implement. Yes. But the task one, this is the fun part. This is the part that you will enjoy. It will be very easy for you, for sure. No. No. Okay. If there is no more questions, we will end here, and we will do we will either have on Monday, we will have the Bitcoin lecture, or we will have a PhD student presentation on Monday. So for Thursday, we will not do a lecture, but for Monday, we will. So the Monday 29th, it's not Easter then. No. Yeah, so on the Monday 29, we will do a lecture, and we will also have the project for you. So the lecture, I will share the papers that I wanted you to read beforehand, and then yeah, either we will do that paper, or we will have a PhD student that will have a presentation. So all right, I guess we can end there, and we will see each other on Monday. Okay. Yes. Okay. Bye bye.